Okay, so today finally we'll talk about this horrible beast called the monad, right? So, who knows what a monad is? Yes, what is it? People are eating here.
What's the problem?
Okay, chew it, yes.
It's a type class implementing bind and return.
Okay, it's a type class implementing bind and return. So that doesn't tell me anything about the nature of monad, right? What is the...
So the way I explain monads to people who have a background in object-oriented programming is a monad is a generic type that allows you to amplify the ability of another type. Right?
Okay.
So, for example, I have a type int. I want to make it nullable. Nullable
okay.
int. I have a type int. I want to make it lazy int.
Yeah, I call this embellishment.
Yeah.
Right? You take a value and you embellish it inside a monad with a monad. Right. Anybody else? Some insight into what monad is? Oh, yes?
It lets people use Haskell like an imperative language and say do this and that.
Ah, okay. It lets people use Haskell imperatively. Okay.
Giving you another shot.
Yeah?
It allows a calculation to depend on previous calculations.
But this is like everywhere in Haskell, right? The previous calculation returns some value and the next calculation takes this value, right? It's called composition, functional composition, right?
I mean, you can compose just going to this type, but you can't make decisions until...
Okay, no, actually this is very close to what I was going to say. Yes.
Have a gold star.
Anybody will tell me that it's about side effects or impure or something like that? Because people keep saying, first of all, a lot of people who don't know anything about Haskell say monads are impure. These are not pure functions anymore. You introduce impurity into Haskell using monads. Is that true? No, it's not. It's the imperative propaganda.
Could we say that a monad is some kind of mathematical object that obeys certain laws, which makes it useful in certain ways?
Useful for what?
Oh, you name it. All kinds of things, but I mean, there's the obvious ones like the ones that are in all the books, IO or reader, monad, writer.
No, I mean, yeah, that's true. Monad is very useful and it serves many different purposes, right? But that's why people are so confused about what is really a monad, right? Because it can be used in so many different contexts that seemingly have nothing to do with each other, right? And another myth is that, and there are actually questions about it on Quora, asking how does monad, encapsulate side effects? Side effects. Does monad encapsulate side effects? Okay, I'll say no. Okay? No. Monad does not encapsulate side effects. This is not true. I think the confusion around monads is because it's a hard concept to understand from code examples. You see one example and it's exception monad. Another one, it's a state monad. Another one, it's a IO monad. Oh my God, what they have nothing in common, right? So many different things that use the same notion of a monad. This is why people say, you know, a monad is a burrito, and all kinds of nonsense like this. And especially the thing about side effects. And there is an element of truth in it, because monads are most useful in dealing with side effects. But they don't deal with side effects themselves. Okay? And everybody who learns Haskell at some point has this like religious experience. Oh, I get it. I get the monad. Okay? And they immediately write a blog post.
I got it.
Okay? Or a tutorial and so on. I'm guilty of that too. Okay? Yes.
You wrote the best one.
I don't know. I wrote some kind of tongue-in-cheek tutorial at some point that compared the monads to what was titled the Tao of
Tao.
monad. The Tao of monad, yes. Because like, you know, a monad that can be described is not the eternal monad. So that's what you get from reading all these tutorials. They try to get to the essence of the monad and they fail. They always miss, right? So it seems like you just get it at some point, right?
I
Yes?
don't know that mine's a definition, but I always think of a monad as providing a context for the execution of the sequential logic execution.
Context.
It's kind of
Okay,
this-
it's kind of like using the term object in object-oriented programming, right? Object, contents.
I want to agree with him. I mean, I
Yeah?
think that
Okay.
what monads are used for, and
Uh-huh.
my question is whether you really need monad or whether applicative or just a functor will do, is you write some code that's pure, and then you beam it up, Scotty. Beam it up to wherever it needs to go.
I see. Okay. Okay.
It's just the way I think of it.
So let me start with side effects, okay, and these impure calculations and so on, because I want to get to the bottom of this. Okay, why do people think monads are used for side effects? And the truth is that actually monads were first introduced into programming from category theory by trying to understand how to implement side effects in a pure language. Okay? So this was Eugenio Moggi who wrote this seminal paper about monads in programming. And he considered a few examples of what normally is considered impure functions that are used in programming, in imperative programming, some impurity, some kind of state that's there, or you know, these computations that do something that's not really functional, right? So let's go through a few examples. The first example is called a partial function. What's a partial function? It's not a function really, but it's sort of like a function, but it's not defined in all its domain, not for all values in the domain. So it's defined in some kind of subset of the domain, right? How do we implement something like this in programming? Well, we have a function that has some big domain, and if somebody calls it with the non-appropriate value, something that for which it's not defined, like calling square root with a negative number, right? What happens? Well, there are many ways. I mean, you can like terminate the program, right? Or you can throw an exception, right, and bypass some part of the program. So this is how it's solved, and you see that this is not really. I mean, throwing an exception is sort of like not included in the signature of a function, right? So it's doing something that's really not describable in the type system. I mean, the thing in Haskell is that, you know, there is an input to a function and there is an output to a function. They have particular types. And the function is supposed to transform the input to the output. And that's all, right? It's a mathematical function. So let's write it down. So we have a function from A to B, which is not really a function. Let me call it with this arrow with a little p, this partial function, right? A partial function. Can we replace this partial function with a pure function? And the reason, the answer is simple, you know. Why don't we just return something that can be nothing or something, right? Let's return maybe. Maybe B. Okay? So we took this B and turned it into maybe B, encapsulated inside the maybe, and now we have a pure function. It's defined for the whole domain of A's. Every A will produce a result. Some of these results will be nothing, and others will be just. Okay? So that's a way of turning this kind of side effect into a pure function. Another side effect, and that's really, really used all the time, is being able to having access to some kind of external environment. So you have a function from A to B that has access to some environment, right? And the signature doesn't tell you that this function can read from the outside. Okay? So how can we make it pure? Well, the way to make it pure is just to pass the environment to this function, right? Together with A. So it really takes two arguments, A and the environment. So let's pass a pair A, E, and produce a B. Okay? Well, this looks kind of different than this. Here we are encapsulating the result, and here it's actually a kind of different argument, right? But don't worry, we know about currying, right? So this is really a function of two arguments, A and E. A function of two arguments can be also written as A, arrow E, arrow B, right? The same thing. Well, it's curried, okay? But it's a function of two arguments. So it's a way of seeing a function of two arguments as a function returning a function. Oh, and we can even put parentheses here to like stress this fact that this is a function returning a function, although they are redundant, right? Okay. So let me erase this and write it here. A goes into E. It sort of has the same form, okay? We are embellishing the return type. What about state? Okay, state is sort of like environment, right? But it's mutable. Okay, can we turn it into a pure function? Well, we can do that. We can first of all we can pass the state to the function just as we did here, right? But since it's modified, it can modify the state, we have to return the new state also at the end, right? So it's really a function. Okay, I'll write it here on the side. It's a function that takes A, comma, state. So state is some type S, and returns B, comma S, a pair.
F prime.
That's prime.
No, type. It's the same type. Right? The type of the it doesn't change the type of the state. Just picks one value from here and there's another value. Could be another value, right? Now, so again, let's query this thing, right? So it's a function that takes A and S and returns a pair, B, S. Okay? Great. Now let's put some redundant parentheses here. And we have again this version where you have A goes into some embellishment of B. So this is a state B. So we start with some computation that computes B, but it has access to state and modifies it, possibly, right? Well, modification, mutation, of course, in Haskell does not exist. So what I mean by mutation is really creating a new state using the old state and a delta, right? That's how we do. We have these persistent data structures that, like appending something to a list. No, prepending, right? Yeah, it's cheaper. Appending is expensive. Okay, another example, and this is maybe a little bit harder to explain because it's normally explained as indeterminism. So a function that's indeterministic, that it actually can return one of many results, right? And every time you call it, it returns something different. Okay, so that's definitely not a pure function. So it will go from A to B, but it's indeterministic. So for instance, think about writing a program that plays chess, let's say, right? So when you are planning the next move, you have to evaluate also the move of your opponent, right? And the move of the opponent looks like a non-deterministic thing. You cannot anticipate what move he will make, or she, right? And also, you have to write this program anyway in such a way that it knows how to respond to every possible move of your opponent. So instead of, returning a new value every time, why don't we just return all possible values at once, right? Even if there are infinitely many. In chess, there's only a finite number of possible moves, but in other cases, there may be infinitely many possibilities. But Haskell is lazy, so we are not afraid of infinities. Okay, so this is simple to implement. We'll just have a function that takes an A and returns a list of B's. Okay? Maybe even infinite list, depending on. But it's a list, right? So all these expressions here, they have the form, and I'm gonna write this in this way. They all have the form A, and what do we do with this B, okay? Well, we encapsulate it. We create a new type from B. So we have some kind of type constructor. Let's call this type constructor M, anticipating the moment. Don't tell Anton. So there is some kind of type constructor here called M acting on B. So here this type constructor is maybe. Here this type constructor that takes a b and produces a function from e to b, we called this reader, right? That was called a reader. Reader e a. Well, let's change this b to a just for readability. So we have maybe a, reader e a. This we will call state. Okay, so this type constructor will be called state and depends on the type of state and this free parameter that we're renaming to a. Okay, this obviously is a list of a as a type, right? So these are the examples of this type constructor. We also know that these particular type constructors are functors, right? Actually, we don't know about the state, right? State. You have to show it, right? You have to show that state is a functor. Okay, so first of all, the definition of state. Okay, state as a. So I have to put data here. Okay, state as a equals. Let's call the constructor, the data constructor, the same name, because we already are used to this confusing thing of being really skimpy with names, right? So state, and what does it take? Well, it has to take a function like this. So it takes a function s to bs. Okay? Just like reader was taking a reader of e to a. Right? The data constructor actually encapsulates this function. So the type constructor takes s and a and produces a new state, a new type, and this type has this data constructor. So we are encapsulating the type b as a function that returns a pair of b with state. It's a function that takes state and returns a pair of b and state. So every time we call such a function, it produces another function. Okay, and I wanted to show that state is actually a functor. So how do we do it? We have to write like instance. I'll use a different color because this is sort of a side remark here about functors. I just want to make sure that all these things are functors. We'll see later why. So instance, functor, and the type constructor. In this case, the type constructor is state s. So I'm already providing one type variable, so it's really a type constructor that needs another type variable. So it's a single argument state type constructor. Okay, where we have to define fmap for it. In order to prove that this is a functor, we have to be able to define fmap, right? And fmap takes some function, let's call it g, yeah, okay, g. And now the second argument is the state s, a. So we pattern match it to its constructor. and its constructor has this function s to bs. Or actually, this is a. Sorry. A. Renaming things always tricky, right? So we are pattern matching it to state, which is this data constructor, and internally it contains a function. Let's call it f. Okay. So, and let me just write down the types below so that we know. So g is supposed to be a function from a to b, right?
Pardon? Why is it A and not B? The one you just changed?
This?
Yeah. I thought it would have been B. And I thought the reader would have been B also.
No. So this is a function from a to b. And this is a type constructor that takes a b and this function, it turns it into a function, right? Now here I rewrote it, forgetting about this first a. I'm just talking about this part, right? So I'm calling this state of b. But in the definition I want to say state of a, just because, right? I mean, I could change it to b. But the only thing important is that this is the same as this, okay? Whether I call it B or C or D doesn't matter, right? I'm just renaming this variable because it's a type variable. Okay, so the type of G is from A to B, just like in every functor, right? There is a function from A to B, and then there is a type. This type is state SA, right? But internally it has a function. So let me write the type of this f. So this is a function from S to a pair AS. Okay? And what we want to return is, again, a state of some function f prime. So let me just write it first. We'll do it in small steps, right? So that every step is understandable. So it has to return a state, and to construct a state I need a function. Let's call it f prime. What's the type of this function? Right? This function, okay? So the type of this function, f prime, is, again, s, but here we put b, right? Because we have a function of from a to b, so it will turn state EA into state EB. And state EB contains a function from S to BS. Right? I mean, it's a little bit convoluted, but really this is the only thing that we can put there. Right? So this f prime is this function, this f is this function, this g is this function, right? And we are moving from A to B under our functor, right? Okay. So we need to create a function here. So we have to create on the spot a function, right? A function that takes state. Mm-hmm. So how do we do this? How do we create a function on the spot? Okay, using lambda, right? Lambda is now known in almost every language what a lambda is, right? But it's really from lambda calculus and from Haskell through lambda calculus, right? So we will do, well, so let me just write f prime is equal to lambda, a lambda function that takes s, and here's it's a value, right? Just to confuse you. This is type, this is value. Maybe I should name it st, okay? Okay, not to confuse too much. So it's a lambda that takes st and produces a pair of, well, D and some ST prime, right?
G of A.
Yeah. So let's see, what do we need here? We need this B. How can we get this B?
We have to apply G.
Well, we can turn A into B using this function G, right? But we also want to use F somewhere, right? And F is a function that requires state. Oh, but we do have a state now. Inside this lambda, we have state, so we can really apply F to this state. So let me see. Let me say that some kind of A prime S prime equals F applied to ST. All right. So F applied to ST will produce me a pair of some, some A and some ST prime. So these are values. Okay. But now I wanted B, right? So really I want to apply G to this A prime, right? Why do I call it A prime? F acting on ST produces me this value of type A and the new state. Okay? So I can apply G to this value A, and this will be of type B, right? And pair it with this ST prime, right? And this will be of the type BS. This is exactly what I want. Okay? So I have a function that takes state and produces a pair of type BS. Okay? This is like, little Sudoku, where, every move is or Tetris. They sometimes call it the Haskell Tetris, because there's only one way of matching these things, right? So now that we have the idea of how to do this, I don't know where to write it. Let's forget about this and just now that we know how to do this, right? Let's recreate it. And we'll see if we understand what we mean. Okay? So this is state of a function lambda that takes a state, right, and produces this pair. Okay. Well, this pair was obtained by acting with F on state. So normally we would like to create some kind of temporary variable for it, right? Because now it's getting too complicated, too many things, right? So let's do it in little steps. So how do we define a temporary variable? And it's not really a variable because nothing is variable in Haskell, but traditionally it's called a variable. It's really a binding of a new name to something. So we use the let. Normally we would say let statement, but that's really not. Everything in Haskell is an expression rather than a statement. So let is an actually expression that returns some value, right? So let, and we are giving a name, let's say AST, for instance, equals, and here we're applying F to ST, right? But now, this AST is a pair, right? It's a pair of A and state. Okay? So in a let statement, we can actually do pattern matching immediately here. I mean, I could use first and second to unpack this thing, but it's much easier to just put a pattern, and this pattern would be some A and some ST prime, right? So I'm unpacking the result of F acting on ST into a pair. So, yeah, am I right? F goes from S to a pair of A. Okay. Right. So I've done this. Now I want to apply G to A. Okay? I want to apply G to A. And let's call it also something else. So in the let statement, I can have several definitions. And in fact, every next definition can use the previous, the ones defined in the previous one, right? They are in order. So if this says A ST, I can use this A immediately here, right? And let's call it B, right? Because it's of type B. So they have to be aligned when you type stuff, right? Here. B. And now we want to finally create the expression that will be returned from this, right? So we say in. So the let expression is let in, right? Under let we define these things, and in we write an expression in which are using these definitions, right? And we want to return a pair B and ST prime, the modified state, right? F modified the state. We want this modified state, okay? And I probably have to close this parenthesis, right? So I'm creating a new state using a function that takes state and applies the function f to the state, produces a pair which has A in it. I apply G to this A to get a B, and I finally return B paired with the new state. Okay? So this is the kind of Haskell Tetris that we usually do. Not all. I mean, this is in these situations where we are doing some really complicated data structures that contain functions. But I wanted to show you that this is possible.
And this is why people call it category theory, because they do the same Tetris.
Yeah, it's just matching the ends of arrows. The end of one arrow at the beginning of another arrow. So, the problem of side effects is solved by this. Okay, this is the pattern for all these side effects that I listed here, and there are some more that there is I/O also. We'll talk about it. By replacing something that says a form from A to B, a function from A to B, which is impure, maybe you shouldn't call it a function, with a pure function that also takes A, the same A, but embellishes B using some type constructor. Yes?
So you still haven't used anything other than a functor.
And actually I didn't use the fact that it's a functor. I just mentioned it, that these happen to be functors. Okay?
Well,
I never used it. I just proved that one of them is a functor, and the rest we know that they are functors because we dealt with them before. But I haven't used the fact that it's a functor.
I think you will use the fact that it's a functor.
I will use this fact eventually. That's why I want you to know that these are functors, right? But here we are only saying that this has to be a type constructor. Doesn't have to be a functor. It can be a type constructor. And we are solving the problem of side effects. Problem of side effects is solved by introducing these functions. These functions are, by the way, called Kleisli arrows. Because there was this guy Kleisli in Switzerland who invented them. Okay?
And they're factor shares?
No. No, I'm just, I'm not an inventor. I'm just passing information from other people, gathering the information in a big heap and then portioning it out. That's all I do. So M is a type constructor, so we could even say M has a kind star, arrow star. Right? It takes this B and produces an MB type 2 type. Yeah?
To prove that that's a function, then we need to prove that the ID F0
Yeah. I should prove the axioms, yes, yes. But I'm too lazy, right? I mean, it's a homework.
exercise for the reason.
Yeah. Okay. So, now. You see, side effects have nothing to do with monads, right? Did I mention a monad here?
No.
It
Did
was
not.
only in secret. Right? This letter M suggests something. But no, side effects are solved by using Kleisli arrows. So where does the monad come from? So, and this is because of the essence of all programming. The essence of all programming is being able to split a big problem into smaller problems and recompose the solutions to smaller problems into one big solution, right? That's what we do for 8 hours a day, 5 days a week, right? Hopefully. I hope you don't work on it. So we have a solution, but it's not composable. And if we want to write a library of functions that have a particular side effect in mind, let's say like functions that produce a maybe, or I showed you before, remember this example with safe, square root. These are functions that produced either. And either is also a functor, and either is a type constructor. If you fix the left side, you know, it's a functor. But with either we had this problem of composition, right? Remember the safe square root? I said if we want to be able to compose these things, safe square root has to also take an either. Because it could be a result of previous calculation, right? So safe square root was taking either and returning either. And then we can compose functions like these using what? Just regular function composition, the dot operator, right? The dot operator, we could compose such functions one after another because the output of one function has the same type as the input of the other function. In this case, an either string or double in our case, right? But the problem with this solution was, I mean, I didn't give you many examples, but if I gave you like 100 examples of this, you know, you would see that something is really annoying. Not wrong, just annoying. Tremendously annoying. Because in every such function, the first thing that happens is we pattern match on this either, right? Decide whether it's left, and if it's left, then we return back left and do nothing else. If it's right, then we extract the value and pass this value to some calculation that takes this value, right, and returns an either, because it may fail in some way, so it returns an either. Okay? So this part of the code where we do pattern matching and short circuiting for left and for right, doing the actual calculation, that's boilerplate. That's something that will be everywhere in our code, in our library of safe functions, let's say. Okay? We don't like that in Haskell. We don't like that in programming in general, boilerplate code. I mean, probably in C++, somebody would say, oh, let's write a macro, because it uses a macro. Yeah. But in Haskell has this power, tremendous power of abstraction. So we can say, hey, this pattern, how do we abstract this pattern? Okay? And it's possible. Okay? Because this pattern sort of is like in between the functions. It's like one function returns an either, and then the next one does something with this either. So it's like between this something and the actual calculation. The actual calculation, remember, was taking a square root of some number. That was the actual thing that we wanted to do, plus this boilerplate. So let's remove this boilerplate, this code, because it's common, and put it between functions. Okay? What's between functions?
Dots.
Dots? But in this case, it's not really a dot because it contains some code, right? And the types would not match. So we have to come up with some different composition of functions that's more general than the dot, right? We want to be able to compose Kleisli arrows. Okay? We want to write something that sort of behaves like the dot, but works on Kleisli arrows. So the dot works on functions like A to B, and give me a function from A to B. Well, actually, it was like inverted, so it was from B to C after a function from A to B, and it produces a function from A to C. That was the dot. Signature of dot. Okay? We want to replace these functions with Kleisli arrows. So, and also flip these two things for some reason. I mean, we could define this operator backwards or forwards. It's more popular to do it forwards. And this operator that combines Kleisli arrow is technically called a fish. See, this is the tail of the fish. This is the meat that we eat, and this is the head. Okay. So the signature of the fish. Sounds like Monty Python, right?
It is Monty Python.
Oh, okay. So we will do this flipped. So we'll say, okay, give me an arrow Kleisli arrow from A to NB, and then give me a Kleisli arrow from B to MC, and I will return you a combined thing which goes from A to MC. Okay? And that's called the fish. And there's also the inverse fish that goes the other way. Right? But it's not used very much. For some reason. So, if we want these things to be composable, we have to define the fish operator for each of them. And for each of them, the fish is different. There are different kinds of fishes. So as an example, this is really a good example, useful example. Let's do the list. Okay, this guy. Let's define a fish for a list. So the type signature, we would replace M with list. So we have a function from A to list of B, right? And another function that takes B to list of C. And we want to produce a function that takes A and returns a list of C. Okay, that's the type signature for it. I just replaced M with a list. Did I forget? Yes. Thank you. So now I'm going to. Sorry, this is not this. This is this guy, right? So this guy, the fish guy, for list takes a function. Let's call this function f. So that's this function. This we will call this function we'll call g. Right? So this is f. This is g. Two functions, and this is an infix operator. This is why I put parentheses to make it a prefix operator. But this is an infix operator, so they go on both sides. It's very nice to have this. And it should return some kind of function, right? So if it's supposed to return a function from A to C, to list of C, we have to define this function on the spot, right? So let's define this function on the spot. So it's a function that takes an A. Okay, so now we have an A, and does something with this A. Okay, but has to produce the list of C's. Okay, now F, we can now apply F to A, right? I mean Tetris now. Okay, what can we do with this A? We can apply this function f to A, and we'll get a list of B's. Okay, so let me just accumulate these things here in the let statement. Let B's, fishes and bees. Let B's equal f acting on A. Okay. So now we have B's, and we have a function here, G, that takes a B and turns it into a list of C's. Okay. So how we go from list of B's and apply a function that takes a B to a list of B's? Fmap, right? Or map. Map. In particular for lists, fmap is called map. But let's be just general and say, okay, we're applying fmap, and we are fmapping this G over B's. And what we get is a list of C's, right? But it's actually So,
what's
so
happening with this?
each G produces a list of C's, right? We're applying to a whole list of B's. So each B inside these B's will be turned into C's, right? So it will be a list of C's. So I'll call it CSS, double plural, because this is a list of lists. Okay? So CZs. Oh, sorry. This is the continuation of this let. Okay? I'm running out of space. Sorry. So this is let, and here we have B's, and here we have underneath we have CZs that we have obtained by F mapping G over B's. Okay? But our function that we are constructing is supposed to take A into a list of C's. And we don't have a list of C's, we have a list of C's. Join. Join. Okay, I'm not gonna talk about join yet. I'll mention it later. But I will just say that there is a function called concat. Right? So,
Is that one generic?
No.
no.
Just for
Concat is only for lists. So concat C's. And that's what I'm returning, right? So I'll get a list of C's from a list of C's. So it's just like concatenating all these little list C's into one big list. Right?
That works on multiple these days, but I think that's
Yeah?
yeah.
Ah. Nice. Okay, but now that we've gone through this process, right, we can be clever and we can simplify it. So it will look like we never went through this process and we came up with this beautiful point-free solution. Let's look at it. Okay, so we are concatenating CZs, right? But CZs is F map of GBs. So we can replace CZs with F map GBZs, right? But F map GBZs, well, BZs are just FA, right? So why don't we say F map GFA? Okay, but this looks really like a composition of concat with F map G, which is now it's partially applied to G, right? F map partially applied to G still requires a list, and this list is provided by F. Okay, and we don't need this lambda. It's just a you know, F arrow G is equal to concat.fmapg.f. Right? We have like canceled these A's both sides, right? So concat fmapgf. And now we erase this so that nobody can see it, right? And we say, oh, this is obvious. It's concat fmap g.f. That's so obvious, right? Can't do anything else. Alright.
Make the dot after the concat.
Well, okay, I'll make it bigger. Both dots bigger. Okay, so that was the fish operator for this particular functor, the list. And now you see that it really has to be a functor in this case, because I'm using fmap, right? So this is where this functor becomes useful. So we have a way of composing Kleisli arrows, right? But remember the dot operator. The dot operator had more properties, some interesting properties, right? The dot operator not only was able to, compose two functions, but it also had a unit, right? So dot can be treated sort of like multiplication or addition or something, some operator, that has a unit, which was ID. The function ID served as a unit. So this guy should have a unit too, if we want it to be just like dot, right? So, but the unit in this case would be of a slightly different signature, right? It would have to be one of the Kleisli arrows, sort of a unit Kleisli arrow. So it would have to have the signature A goes to MA, right? The same type here and here. And this unit is called, for some reason, it's called return. Okay? Because, I don't know, because maybe to imitate imperative programming. And that's also very confusing to a lot of new Haskellers, because return, I know what return is. It's used in Java, C++, C, okay, so I know, but no. That's a different return.
Why don't we just call it Kleisli return or Kleisli ID?
Actually, there is a different name for it. It's called pure. Yeah, pure is probably a better name. But when you see actually do notation and you see return there, it really looks like imperative return that you would actually put there. So it reads much nicer with return. Okay.
Pure is defined for applicative or for functor, I guess. Not for, but it's going to be the same. Yeah, it's the same.
The applicative has the same thing called pure. Okay, so we have to define a fish, and we have to define return, and this return is different for each of these cases, right? For instance, what would it be for maybe? Okay, so it would return
Just.
Yeah, exactly. Return X, so we are providing something of type A, and it should return something of the type maybe A, right? But what should it return? It should return just, because it imitates identity, right? What you give it, it returns it, but it just encapsulates it. The most trivial way, encapsulate. Now, if we returned nothing, that's the other possibility. Why not nothing, right? You would break the monadic laws. No, actually, what you would break here is the unit property that composed with a fish. It should return the same, right? Well, this is a monadic law. But anyway. So this is for maybe. For reader, return X equals, and we have to create a reader from nothing, okay? Reader. And to create a reader, we provide a function from some environment E to A, right? So lambda E, right? And it should return A. Okay, well, we have here X. Let's use it. Now we are ignoring the environment. This function actually doesn't need access to the environment. It ignores it, right? So it's a function that ignores the environment and just returns x. It's almost like identity, except that kind of encapsulates it into a function. But this is the closest you can get to identity. For state, very similar. It will state, and again lambda st, right? And now it has to return a pair, okay? A pair of x. That's something of type A that we have at our disposal. We don't have anything else, so we have to put x here, and we return the same state, right? So it's a function that takes a state, ignores it, no, not ignores it, just returns it back, doesn't modify it. Right? It's unmodified state, just pairs it with the value that we want. Okay, what else? List. Huh? Return takes any value x of type A and produces a list. Well, there are actually several possibilities, but the simplest thing is to just return a singleton list. That's a singleton list. If you put a value between brackets, that means just a one element list with this value. So that's like the simplest thing that we could do. What is another possibility?
No. No.
Null would be bad because it would not identity.
That would be equivalent to return x equal nothing for
Yeah.
maybe, right?
Yeah, it wouldn't do.
So n some number of repetitions of x.
How big a number?
What a 10.
Infinite. Infinite is such a nice number, right? Infinite number of x's. Yeah. A kind of stream of x's. Yeah. I think there is a function called duplicate that produces an infinite list.
Yeah.
Right? So we could do this. It's not a monad though. But it is an applicative. We haven't talked about applicatives, I know. Just anticipating stuff. Okay, so one final thing, okay? If we want this to be really, really nice composition that has identity, we want it also, well, so we want this to be an identity, which means return fish any function, any Kleisli arrow should return this Kleisli arrow, right? So that means it's a left identity for Kleisli arrow. It also has to be a right identity for Kleisli arrow. So with return here equals f. So these are just unit laws, right? They have to be fulfilled if this is supposed to work like identity. And the other thing that we require is that fish is associative, just like dot was associative, right? So f fished with G and then fished with H is the same as f fished with G fished with H. Okay? So that's associativity, that you don't really need these parentheses. It says that whenever you put the parentheses, it doesn't matter. Okay? So, let me quickly define a monad then. A monad is a type constructor, right? This M. A type constructor with a fish defined for it. So you know what the signature for fish is, this. And return with this signature. So these two functions, this is a higher order function because it takes functions, right? This return is just a regular function. These two functions have to be defined for it to be a monad. And on top of this, something that you cannot express in Haskell, but these are the laws of monad, these three. And they're so natural, right? I mean, it's like obvious, okay? And by the way, this kind of structure, when you have sort of a generalized multiplication and you have some kind of unit, neutral element, and it's associative, it's called a monoid, right? So a fish forms a monoid, or a monad is nothing else but a monoid in the category of endofunctors. I said it. All right, let's take a break.